Hello everyone, my name is Mohammad Hekmatnejad and I'm going to talk about search-based test case generation by monitoring responsibility safety rules. This is a collaborative work with Dr. Georgios Fenekos, who is my PhD advisor at the Cyber-Physical System Lab at Arizona State University, and Dr. Bart Hoxha, who is a former lab mate and now a researcher at the R&D department of Toyota Motor North America. What I'm going to present in this talk is generally about simulation-based testing of automated driving systems and more specifically search-based test case generation using formal specifications. Deep learning is widely adopted in ADS, which highly relies on real driving scenarios for training and testing purposes. However, in an open environment, we mostly and usually drive optimistically. That means even though we might not end up in an accident situation most of the time, our driving behavior should not be considered as safe behavior just based on that fact. Therefore, we need to artificially engineer test cases that put the system in situations that are less frequently happening while do not violate some assumed guarantees. Additionally, if there are real scenarios that need to be investigated for determining the reason for failure, for example crashing, and who should be blamed for that, we can simulate and monitor the performance of the system concerning some design and system requirements. In simulation-based testing, we can exercise the boundary behaviors between safe and unsafe situations and ignore the cases that are not relevant. For example, watch the video of an accident that happened for a Waymo car in Chandler, Arizona. You can see the other car in the opposite lane crashed into the Waymo car, while the autonomous car did not take any action to avoid it. Shall we consider this accident as a failure for the autonomous car as well? We argue that no. We should not consider the cases in which an autonomous car has no control whatsoever to change an unsafe situation into a safe situation. The other possible crash scenarios that are shown on the right side of the screen also are not relevant nor interesting for testing purposes. In short, our claim is that for efficient and effective testing, we need to detect and robustify boundary situations for which adversaries are needed to exercise the boundary behaviors between safe and unsafe scenarios. One way to ignore irrelevant scenarios is to use responsibility sensitive safety rules, or RSS in short, for testing the safety of an ADS. RSS rules are developed by Intel Mobileye to capture safe driver behaviors for automated driving systems. Alternatively, we can use the RSS rules to decide if, for an accident, the blame should be put on an ADS or not. On the right side, look at a driving scenario with two cars. For each, their longitudinal and lateral safety boundaries are highlighted. According to the RSS rules, if a safe situation, for example no overlap among the car's safe boundaries as it is right now, becomes first laterally unsafe and then longitudinally unsafe, after a threshold time, the black car, which is in back, has to brake longitudinally to avoid colliding to the front car in yellow. In continue, I will introduce and use sample requirements of this nature to produce desirable test cases. The RSS rules serve two purposes in this work for testing the safety of an ADS. First, we can use them to generate test driving scenarios that exploit the RSS rules as a guide for optimal sampling in test generation. Second, we can use the rules to quantify the safety robustness of autonomous driving controllers. Note that we can also combine these two as well. Next, I'm going to minimally introduce safe longitudinal distance and response for one-way driving scenarios. The safe longitudinal distance, as is shown in the top graphics, is a minimum required distance between the front and back cars such that if the front car in yellow brakes with a maximum braking deceleration, A-lon max brake, and the back car does not accelerate above a maximum acceleration A-lon max accel during growth seconds as response time, and then it brakes with a minimum braking deceleration A-lon min brake, they do not collide with each other. You can see in the below animation what I just said about safe longitudinal distance. Now I'm going to minimally introduce safe lateral distance and response for one-way driving scenarios. The safe lateral distance, as is shown in the graphics, is a minimum required distance between the left and the right cars, such that if the right car in yellow moves toward the black car on the left with a maximum lateral acceleration, a lat max XL, and the black car does not accelerate above the same maximum acceleration during row seconds as response time, and then they start steering outward with minimum braking deceleration a lat min brake. Then they do not collide with each other, as you can see in this animation. Let's get to the solution architecture. We have 5 steps in our proposed architecture, as you can see in this flowchart, which I'm going to explain using some other diagrams. In the first step A, we need to configure the test environment and initialize some desirable test case templates. We use the Simatov framework, which is developed by my former labmate Erkan Tukali as our simulation control unit. In Simatov, VBots is used as a simulation engine. Also, Simatov is equipped with some controllers for autonomous driving. Next, step B, we configure the monitor with the formal requirements that are going to be used for evaluating the quality of the sample generated test scenarios. The other 3 steps will be executed in a loop. The more detailed and color-coded diagram for these steps is shown here. We use a sample test case generator that can work in uniformly random mode or optimized mode. The sample generator can be part of Simatov or the robustness analyzer. After a sample test was generated, the initial configuration of the objects in the environment plus the trajectories of the adversarial vehicles will be passed to the simulator. Next, the simulated scenario will be returned and then passed to the pre-post processing unit for coordination, translation, and synchronization purposes. The result is ready for monitoring against the formal requirements, which are the RSS rules in this case, using TP Taliro monitor as part of a Staliro tool. This process continues either for a fixed number of iterations or until a minimum required quality for tests is computed. In order to demonstrate the usefulness of the RSS rules for test scenario generation, we here represent a very simple specification for avoiding a collision. This rule, which is denoted by phi CAS or case, which is in signal temporal logic, requires the boundaries of any 2 cars not to collide with each other. On the other hand, as a more sophisticated safety requirement, we use the RSS rules only for the ego car. We have already translated the RSS rules in signal temporal logic in a previous work published in the Memo Code 2019. Now it's time to see the result of using what I explained so far in a case study. As our test scenario environment, we created a straight road with 3 lanes in it, and there is a stop sign on the right side of the road which is not effective. Also, there are going to be 3 cars driving in this road. The yellow car is the ego car, for which the initial position, orientation, and speed are sampled through various methods such as uniform random sampling or biased sampling through stochastic optimization. For the blue and red cars, which are adversaries, all the initial conditions plus their whole trajectories are generated using various methods, as I mentioned before. Let's see the simulation of a sample test scenario in action. In the next slide, I'm going to talk about the usefulness of this test. Here you can see the colored mesh trajectories of the 3 cars that you observed in the video in the previous slide. Also, I have chosen 4 snapshots labeled from B to E and use them here on the trajectories for highlighting the relative positions of the cars. One might think that the reason for considering this test as a useful test probably is because of the lateral dangerous distance between the ego car and the blue car at the beginning of the test. However, This is not true because the initial position of the two cars violates the assumed guarantee condition of the RSS rules, which in this case is to have the blue car being driving in front of the ego car. On the other hand, the red car was initially within a longitudinally dangerous distance in front of the ego car. Based on the RSS rules, the ego car had to respect the required maximum acceleration from the time that the snapshot C was taken for row seconds, which did not happen. And therefore, this is a violation of the RSS rules that makes this case an interesting scenario for us. Regarding the reason for the violation, it might be caused by a faulty controller of the ego car, or it can be due to the uncontrollable initial conditions of the ego car. We conducted 3 different experiments. In the first one, we selected the uniformly random generation mode for our sampler, and we generated 1000 test scenarios. For the 1000 test scenarios, 23% violated the RSS specification versus the 60% cases that violated the simple collision avoidance specification, also known as CAS. Additionally, 19 of the tests did not lead to accidents but violated RSS rules. These results confirm and emphasize the necessity of safe driving requirements such as the RSS rules in testing the ADS, since many of these tests selected as worthy by the case specification are not meaningful based on RSS specifications. Also, in the second experiment, we used the sampler in the optimization mode and passed the case specification as the cost function. Based on 1000 tests that were generated by the sampler, we found more dangerous test scenarios. That is, 60% of the tests violated the RSS rules, while 98% violated the case specifications. Again, this stresses the fact that a lot of the tests were not useful based on the RSS specification. Here, 20 tests that violated the RSS rules did not cause accidents. Finally, we used the RSS specifications as the cost function in our sampler, and this time we only ran our sampler 350 times. Among the generated test driving scenarios, we found more relevant cases. The result revealed that 16% of the tests violated the RSS rules, while 85% violated the case specifications, and among them, one test did not lead to an accident but violated the RSS rules. In addition, we can classify the generated test scenarios based on the constraints that were more significantly violated by them. For example, for the first set of tests, we ran without optimization. These two parameters, which are the maximum allowed lateral acceleration and zero mu lateral velocity, were mostly violated. For the last sets of tests that we used the RSS specification as the cost function, the maximum allowed longitudinal acceleration was also among the highest rate of violated RSS parameters. These data can be used for clustering the generated test scenarios according to the underlying RSS constraints and their robustness values. In conclusion, we used the encoded formulas such as the RSS for automated test case generation for discovering control software bugs using our Simoto framework that you can find the relevant work here in this paper. We presented an automated and qualification-based method for generating driving test scenarios. These scenarios could be used for discovering control software bugs in automated driving systems. Also, it is possible to automatically extract vehicle trajectories from YouTube videos to initial these test scenarios that you can find the relevant work here. As part of future work, we are going to translate the RSS rules for other needed driving scenarios such as cross sections and use this extended translation of the RSS model in our search-based test case generator. Initially, I had more slides to present, which I have another recording based on them. Please feel free to contact me if you need the longer presentation and the PDF version of the slides. In the end, I want to thank my collaborators, Dr. Fenicus and Dr. Hoxha, in this work. Also, thank you for your attention. Any questions?